Okay, for 10.8. 10.8, we're going to actually look at the graphs of polar equations, not just polar coordinates. Okay? And polar coordinates, you still had that radius and angle as far as finding where the graph is. So if I have something like this, where I have an equation system, I can essentially do this by plotting points. Okay? What comes first, the radius or the angle? Radius. So r then theta. So the idea is I'm going to plug in different theta values. Well, do ones you know. Think about the unit circle. Okay? If I just look at some easy ones off the unit circle for sine. Well, if I want to find r, then this theta value, well, what's an easy one to plug in to sine? What angle is easy to plug into sine? Yeah, do 0, do 90. Well, 180 will be back to the same as that. That's all right. 270 if you want to do those. Then look at a couple more. Let's look at 45 degrees. Let's look at 30 degrees, something like that. You don't have to do a whole bunch, but just to get an idea of what this thing looks like. Now, if you plug in 0, what's sine of 0? 0, so that's 0. That really doesn't tell me anything, right? What about sine of 90? 1, so that's going to give me -4. -4 times 1 is -4. So if I go to graph that point, 0, 0 is still at the origin because you're not going out at all. You're just stuck on that pole or origin spot. What about -4 90? How would I graph -4 90? Right, 90 implies you're going up, but it's -4, so I'm going to go 4 in the opposite direction of 90. So I end up with a dot right here. 180, you're gonna again get what? 0. 270, well, what's sine of 270? -1, so that's going to give you 4. So where's that at?
No.
Same spot. It's 4 down. So you'll get this showing up a lot where you'll have this repetition going on. Okay? So 4, 270 is the exact same thing as -4 and 90. That's why I want to do a couple more. At 45 degrees, what's sine of 45? Square root of 2 over 2. What's -4 times the square root of 2 over 2? Yeah, -2 root 2. And what's that approximate as a decimal? It's that big? Considering square root of 2 is 1.414, my guess is it's 2.8 something. Yeah. -2.8. And I'm graphing this, so I'm going to call 2.8 good enough. So if I go to 45 degrees and I want to go -2.8, where am I going to go from there? Yeah, you're going to go the opposite direction and almost to 3. So if here's 45, then I'm going to go 1, 2, and then almost to 3. So if that's 45 degrees, 135 degrees then would give you the same thing. But you'd go the opposite direction from 135. So that would end up being 1, 2, almost to 3 here. What about for 30 degrees? What's sine of 30? Half. So I have -4 times 1/2, in other words, -2. So where's that going to be? Yeah, 30 degrees would be right here. So I'm going to go the other way out 2. So that's going to be right here. So then what if I did 150 degrees? Yeah, it's going to be a reflection over that vertical axis. So you actually start to get an idea of what the shape looks like. The problem is you don't know exactly how the progression goes, but it ends up just being a circle with its top, or the top part of it on the origin, and going down how far? 4. Diameter 4. Okay. Now if you do a few of these, you start to see patterns show up like that. That's fairly easy to graph these. And yes, I'm going to let you use a calculator for it though. If I wanted to graph that on the calculator, what would I need to do?
Polar.
Change it to polar. So, go ahead and graph this on your calculator. Make sure you get something that looks like that. So hit mode, go to polar. It's function, parametric, polar, and something else.
-4 sine. -4 sine theta.
-4 sine theta. Oh yeah, you can't see the equation. Sorry. Should it be an ellipse?
Well, no. I'm in standard, so you can do square, right?
So you want to do square. So zoom wise, you want to go to standard to start pretty much. Now you may need to adjust from there a little bit because it doesn't look circular because of the way they are shaping the axes. So then go to zoom and go to square after that. Makes it a little more like a circle. Still not great, but did everybody get that thing? What did you get?
Because you're in radian.
Okay, not necessarily. The newer calculators, it becomes very hard to do this with because if you hit window, if you're in degrees, you want to make sure to have like your theta min max be like 0 to 360. Okay, you want your steps to be 7.5. In radians, that would be 0 to 2 pi and pi over 12 in place for the step. Okay. You still keep the max and min the same. You might want to adjust them a little bit if you want, just to make it a little larger. Oops, and then I just deleted that, 7.5. So if I go like -10 to 10, then I want to change the y to like -7.5 to 7.5, something along those lines, to keep that ratio close. But the biggest thing is that theta value. If you're doing it too much, what the calculator is doing, because of the steps, especially on the newer ones, if I make those steps too big, so if I made this like every 30 degrees, see how I get a hexagon? Because it's plotting individual points and then connecting those points. So if I up this to like 90 degrees, actually no, 90 degrees is just giving me 0, 0, 0, 0, so it's not drawing anything. So 45, something like that. Okay, but in reality, it is that circle. You're just not seeing everything. So you want to make sure your steps are small enough, which about half of 15 degrees is enough, or pi over 12, to get it close. But the newer calculator, that ends up being more severe just because the pixel density is different. Okay? And obviously, what kind of graph would you call that? Circle. The shape's a circle. Okay. Terminology-wise, you don't really have an x and y axis. Your calculator is going to show, if you hit trace, it'll show x and y on here, but that's not actually x and y. As I go around this, my steps are going up by 7.5 degrees each time. I can find where 90, I'm 4 units down, and I'm on that axis. The calculator is interpreting that by position. But in reality, these are different axes. So you can actually look at whether something has a symmetry to, instead of the y-axis, you say it has symmetry to the line, theta equals pi over 2. Instead of symmetry to the x-axis, you say that it has symmetry to the polar axis. So symmetry vertical, or symmetry over that vertical axis is symmetry with respect to theta equals pi over 2. Symmetry to the x-axis is to polar axis. And symmetry with respect to the pole is like rotational symmetry. Does that make sense? They're just using slightly different terminology because x and y don't really apply anymore. Okay. Symmetry-wise, in general, a quick test for what kind of symmetry most likely you're gonna have is if you're doing something to sine theta, it's going to have symmetry with respect to that theta equals pi over 2. Just like the one we just did. If you're doing cosine of theta and doing something to it, it's going to have symmetry with respect to the polar axis, to that horizontal axis. In general, that's what's going to happen. Now, depending on the type of modification, though, the graphs can look vastly different. Because if I add on a 2 to 4 sine theta, half that one on your calculator. And what does it look like?
This little swirly thing.
This little swirly thing?
It looks like this.
Way to describe the view.
I mean,
It should get something that looks like this. Okay? And there's actually a name for this. One thing though, to graph it, I need to find some reference points. So I'm going to hit trace. And I'm going to go around this until I get to some key values. In other words, when one of those X or Y hits 0. So I can see at 90 degrees, I'm 6 out. So I'm going to go to 90 and go out 6. 1, 2, 3, 4, 5, 6. Okay? Then I'm going to keep going around. Now if I look at 210, it's back at 0, but keep going. At 270, it's up at 2. So you can kind of get an idea for the shape of it. I don't expect these to be perfect when you're doing these by hand. So the idea is get those kind of key points. I know it goes through the origin. So the idea is this thing comes around like this. Oops. Goes up to that. Then comes back out and around to here. Okay. Anybody want to venture a guess on the name of that thing?
spiral.
Hmm?
Squiggly.
Squiggly, spiral. How about turn to page 787 of your book? I do expect you to know the different names of these designs.
Oh my god.
In reality, there's not that many there. Which one is this?
Lima cone with inner loop.
Yeah, a Limacon with inner loop. Now, if you look along the top, all those are different types of Limacons except for the one that's heart-shaped, which they call a cardioid. Well, cardiac, cardioid. It's from the same root. You have a Limacon with inner loop, dimpled Limacon, where it's dented in a little bit, convex Limacon. What's your difference between a cardioid and a dimpled Limacon?
One comes to a point, the other one's rounded.
Yeah, where's that point actually at, though?
0, 0.
Yeah, it hits that pole. It hits the origin. Okay, and if you notice, all the ones in the middle are all what?
Roads.
Rose curves. And then you just refer to as how many petals they have. And obviously you have circles, and then your last one kind of looks like an infinity sign. Lemniscate. And honestly, Limacon, Lima bean is how most people remember that. Sort of. It's not great for the inner loop one, but if you can stretch, it works. Okay, so this one, go ahead and graph this one and figure out which kind it is. Yeah.
Do you like know the names of these?
Yes.
Sketch a. I have a question. Sorry. Why is it R? Why is it?
It's referring to the radius. The radius, how far out you are, is based on the angle theta. So that's why it's R. So how far out do I go along the line 0? Along 0 degrees? 1. How far do I go along the x-axis the other way? Or the polar axis?
5.
5. And does it hit the origin?
No.
No, so that makes it what?
Dimpled Lima cone.
Dimpled Limacon. And again, I don't expect these to be perfect, just get them.
So you don't need to do like up and down, for example.
You can. How far does it go up and down?
Around 3.5.
3.5, okay.
No. It goes up 3. Exactly.
No, you're wrong.
No, I'm right.
Okay, let's look at it.
It goes up exactly 3
I disagree.
at that position.
Mine goes up more.
90 degrees, it's at 3. So it goes through 3.
Mine goes to 3.4.
Yeah, that's something wrong with me.
Does it actually give you a 0 for the x-axis when you're doing that?
0 for the X. Oh,
Yeah.
no, I was going like at the highest point.
Okay, that's different though. We were looking at where it crosses the x-axis or the y-axis.
Got it.
So that crosses at 3. So yeah, if I drew this more accurately, Okay. So it stretches out to where you were saying, true. But we were just looking for where it crosses, because that's honestly about the easiest way to draw it. Go a little beyond that and then come back in. So that's a little better. Still not great, but I'm not going to expect you to be exact with this stuff. Okay? Convex looks like it's flat on one side. So, go ahead and graph this one. This is probably the one type you're most familiar with. Line icons are usually fairly new when you get here. This is your rose curve. How many petals does it have? And I jumped to the wrong one. We'll go back to 4 in a second. They're both rose curves. So it's a rose curve, 3 petals. How far out does it go?
It goes 3.
3 out. Which typically this number will give you that reference to how far out it goes with these. And 3 here, I usually think of as 360 over 3. Now this will give you a rough idea that this is 120 degrees to the next petal. So if I'm going to draw this, it's going to look roughly and pretend that I went through more. Roughly like that. How many petals does this one have? How many do you think it'll have?
4. Will it?
2 or 4?
Wait.
The 4 out front is how far out it's going to go, right?
It's gonna have 3, 4, 4, 4, 4,
4. Whenever this is an even number,
4.
guys, whenever this is an even number, it's actually going to be double whatever it is.
What about when it's odd?
If it's odd, like this one was, it's going to be exactly what that number is. It also says that off to the side on 787 when you look at the rose curves, it says that off to the left.
Oh.
Okay? So if it's even, it's always going to be double that number. So it says 4, it goes out 4. And yeah, it actually is on the axes. So, draw your curve. So something like that. It's honestly easier to do it that way and keep it accurate than to do like half and half. Because it will never look right if you try to do like half this way and then do the other half.
Did that the first time.
Okay. Last thing. It's a general flower, so they call it a rose curve.
I was saying.
You're right. It doesn't really look like a rose at all.
Daisy
Or
curve.
something. Yeah.
What about r squared equals 4 cosine 2 theta? How would you graph this one? Square root it. So if I square root both sides. Now, the nice thing here is I actually don't need to put in the plus or minus to do two different equations. I can just do this as one equation. Here's when I graph it. It's one of the Leibniz gates. Now, the newer calculators, you run into a slight issue. It doesn't do the inside part. And it's because the values are happening so fast that it looks kind of screwy. So go in and change your theta step to like 1. Or if you're doing radians, turn it to like do like 0.05 or something. Okay? It'll graph a heck of a lot slower, but should go in a little farther towards the origin.
What inside part are you talking about that it doesn't run?
On the newer calculators, it's kind of like not graphing from here to here.
Oh, mine does.
And that's fine. You may have a window value set that it's doing that. If you do the 7.5, though, sometimes the newer ones will not show you everything. So what's that one called again? Leibniz gate. And let's actually 3, 4.
Or infinity sign.
So it looks roughly like that.
Wait, how do you get these lines to show? Wait.
You make that theta step, smaller. Will usually work for it.
Okay.
Yeah.
Why is that out 4?
Oh, sorry. Yeah, it should be 2, but I honestly couldn't draw it that small. So I said, okay, this is 1, this is 2, this is 3. So I doubled my scale to be able to see it better. So I draw it that small, you're not going to be able to see it at all. And that's actually it for this section. Questions on any of it?
Thank you.
We're not doing 5-9 either. Okay. So, tomorrow, honestly, if you want to think of a second day at 10-8 or think of first review day, we'll just have a couple review days. Test is Friday.